Just get rid of some dead space. Okay, so each, various structures have various chemical shifts. So you can identify the type of structure based on the chemical shift. Additionally, when you see these peaks, sometimes you don't get one peak, you get a group of peaks. Peak splitting. And this happens through coupling between nearby nuclei. So the spacing between the peaks is a constant called the coupling constant, J. And then the bonding electrons convey spin states of bonded nuclei. Spin states of nuclei are coupled if they're near each other. And the alignment of spin states of bonded nuclei affects the energy and excited states of observed nuclei. And so you get a coupling pattern and an intensity that follows Pascal's triangle. So by looking at how things split, you can tell what kind of bonds they are around. So the energy level of nuclei are affected by covalently bonded neighbors' spin states. So this is a 1 bond between hydrogen and carbon-13. This is a 3 bond pairing between hydrogen and hydrogen. So the spin states of covalently bonded nuclei want to be aligned, so you get this splitting into levels and 2 peaks. And the magnitude of the separation is called the coupling constant and has units of Hertz. So you get more peaks, the more things you're coupled with, basically. So if you're coupled to 3 hydrogens, you will have 4 peaks. Coupled to 1, you'll have 2 peaks. So the multiple splits consist of 2 and I plus 1 lines, where I is the nuclear spin quantum number, that's usually a half, and N is the numbering of neighboring spins. So if it's on its own, you'll get a single line. If there's another neighboring spin, you'll get a doublet. 2 neighboring spins, you get a triplet. 3, a quartet. 4, a pentet. So equivalent nuclei do not interact, and the coupling constants decrease with separation, and the multiplicity is given by the number of attached equivalent protons. And if you have multiple spin systems, the multiplicity is NA plus 1 times NB plus 1. And the relative peak heights and areas follow Pascal's triangle, and the coupling constants is independent of applied field strength. So here is an example. If we're looking at the CH2 here, that's coupled to 3 hydrogens over here and 2 hydrogens over here. The B protons are split first by the 3 protons on A, with a J of 7.3 Hertz. And then they're split again by the 2 protons on C with a J of 6.8 Hertz. And so 1 Pascal's triangle, and then the combination. So these are doubly split. And you get a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 peaks. Which is 3 plus 1 times 2 plus 1. So you can use this sort of you can use these sort of patterns to figure out what things are bonded to. And the coupling constant can actually be related to the torsional angle, which can be used to solve structures. So you can get structural information out of NMR studies. So this is a compound with empirical formula C4H8O, and we want to identify the compound. This here is our reference, so we don't need to worry about it. We have a strong singlet at about 2.25 parts per million. This is a methyl next to a carbonyl. There is no peak at 9.7 parts per million, which eliminates aldehyde groups and suggests a ketone. The quartet at 2.5 ppm suggests a methylene next to a carbonyl coupled to a methyl. And the triplet at 1.2 ppm suggests a methyl coupled to a methylene group. So this methyl is split into 3 by the methylene group here. This methylene group is split into 4 by the methyl group here. And this methylene next to a carbonyl doesn't split because there's not any hydrogens on the carbon right next to it. So you're looking at neighbors, but the distance it can only cover is like 3 bonds. There's also the nuclear Overhauser effect, which is an interaction between nuclear spins mediated through empty space, like ordinary bar magnets. This effect gets time averaged and gives rise to this dipolar relaxation, time 1 and time 2, and specifically the cross relaxation effects. So if you perturb the H1 spin population, that can affect the carbon-13 spin population and vice versa. This is the nuclear Overhauser effect. And this can be studied with certain patterns and like 2D NMR measurements. So it's the change in intensity of an NMR resonance when the transitions of another get perturbed, usually by saturating them. So this would be, you're looking at carbon and then you saturate the hydrogen and see how that changes. So you can eliminate a population difference between transitions by irradiating one transition with a weak RF field. So you can ensure that all the hydrogens are in one state. And this leads to changes in the intensity of the other measurement. So the populations and energy levels of a homonuclear AX system with a large chemical shift difference and observed signals only occur from single quantum transitions. And if you saturate this changes the energy levels. And the relaxation can occur through 0 quantum transitions, single quantum transitions, or double quantum transitions. And so the observed NOE will depend on the rate of these various pathways. Well, let's talk about the sort of design or structure of an NMR instrument. There is a spectrometer computer and a host which does master control and timing, hooked to a host computer. This does shim control, and this has shim control, which controls the shim currents and the shim coils around the probe. There's also the lock control, which is lock transmit and receive, and lock preamplifier feeds into the detection coils around the probe, and the gradient control and the gradient amplifier, the gradient coils around the probe, all designed to give a nice control over this. Then there's also the RF control. There's linear transmit synthesizers, linear transmitters, linear amplifiers, sending out a decoupling. Please observe the preamplifier and the quadrature detection and the analog to digital converter, which goes to a digital filter feeding back into the computer. And then there's the VT control and the VT unit. Basically, there are sweep coils, a radio frequency receiver and amplifier, a radio frequency transmitter, coils for those, a spinning sample tube in the middle, and a generator for the sweep. This is sort of the basic schematic. And the transmit and receive coils are more or less the same device in this design. This isn't the case in all designs. So traditionally, B0 is generated by a coil of superconducting wire, which requires a temperature below 10 Kelvin to work as a superconductor. So niobium, titanium, for example. The superconducting coil is cooled by liquid helium, and to decrease evaporation of the expensive helium, the dewar is jacketed by a liquid nitrogen dewar. With our instrument, we have a permanent magnet, making a smaller field, but we don't need this expensive stuff. The source energy for each experiment is an RF pulse through the transmitter's coil. The detector is also a coil and RF receiver. Sometimes the transmitter and receiver have the same coil. Often they're not. So here we have the superconducting solenoid that provides this is, a superconducting magnet. This is the coil of wire that provides the large magnetic field. It needs to be kept at liquid helium temperature. So there's an inner dewar, there's an inner structure. There's liquid helium inside that, and then around that there's a jacket of liquid nitrogen. And this leads, because the wire is superconducting, you get near zero resistance, minimal current loss, and the magnet stays at field for years without an external power source. But it does require cooling. You need to keep the liquid helium and liquid nitrogen cold, and the magnet cold. So standard NMR tubes are they're tubes. We saw some of those. And on many instruments, there's a spinner. This spins the tube to even out measurements, give you a more homogeneous signal. So, it helps eliminate, if you have some spot in the tube or some point in the tube that's not mixed as well or something with stronger concentration or something. Doesn't need to happen, but it can help. And this is especially true in these things where you're dropping this tube far into this into the cold dewar. So, some problems. The field drifts. B0 will change. There also could be an issue where the field is not constant over the sample. So a well-shimmed magnet has a uniform magnetic field along the length of the sample. Poorly shimmed magnet has a varying magnetic field across the sample. And so the chemical shift ends up wider. You get a much wider peak. So you constantly have to shim. Our instrument, for example, is set up so that whenever it's sitting around doing nothing, it's constantly auto shimming and getting this chemical shift as tight as possible, as long as someone remembered to put it on standby. The lock system will correct for magnetic field drift. This is done where the NMR probe contains an additional transmitter coil that's tuned to deuterium frequency. and changes in the reference absorption signal control of feedback circuit and a frequency generator provides a fixed reference frequency for the lock signal. So if the lock signal differs from the reference frequency, a small current occurs in a shim coil to create a small magnetic field to augment the main field to put it back into resonance. We also use a deuterium lock. And shim coils help even out the magnetic field. So these are, these correct for magnetic inhomogeneity. It can be very complicated structure of many coils. And you can change the coil and the current in each coil to even out the magnetic field and get very nice peaks. And the probe is done with an RF coil like this. And you tune, there's a tune and match system, the tune system corrects the differences between observed and desired frequency. And the match system corrects impedance difference between the resonance circuits and the transmission line, which should be at 50 ohms. So you adjust two capacitors until the tuning and desired frequency match, and you obtain a null. Well, you adjust and all this is with a modern system, all this is handled more or less automatically. Now, receiver gain is important. You need to amplify the radio frequency FID signal from the probe. You want to maximize signal to noise. You don't want your gain too big because you'll clip off data and lose information. But you don't want it too low because you'll also lose, that's going to give you lousy signal to noise. You're not going to get a lot of information. So you'd like your gain to get sort of as big as you can measure. And this signal is dependent on sample concentration. So there's sort of a range. You want your analog to digital converter using as much of its range as possible, but you don't want to go beyond its range. So a clipped FID gives messed up peaks and weird noise. If you set the gate appropriately, that noise goes away and the peaks are cleaner. A frequency sweep, a continuous wave measurement to identify resonance, is very slow. We step through each individual frequency. The pulse Fourier transform technique collects all frequencies at once. In the time domain, it's very fast. Time per sweep is 1 to 10 seconds as opposed to 1 to 10 minutes. We will be doing pulse Fourier transform methods. Those are the most common. In Fourier transform NMR, how are all the individual nuclei excited simultaneously? You have short duration RF pulses, which have a bandwidth around a single frequency that's 1/4 the period of the pulse length time. So a shorter pulse width gives you a broader 1/4 times the pulse time. A shorter pulse width will give you a broader frequency bandwidth. So if you do a long pulse, you don't in the frequency, the peak, you'll excite fewer frequencies, but a short pulse will excite more. And generally what you do is a pulse that's long enough to invert or so the length of time the B1 field is on equals the torque on the bulk magnetization. This is the NMR pulse length or tip angle. Generally, this is a measurable quantity. It's instrument and sample dependent. Generally, do something like a 90-degree pulse. So a 90-degree pulse maximizes the signal in the XY plane where the NMR signal is detected. A 180-degree pulse would invert the spin population. No NMR signal is detected, but you can get an effect called the spin echo. And you can generate just about any pulse width desired. And your data is with Fourier transform NMR, you can increase signal to noise ratio by collecting multiple copies of the FID and averaging the signal. But the total experiment time is proportional to the number of scans. So you get diminishing returns. A proper spectral width, you need to be large enough to capture all the NMR resonances. You can have issues with carrier offset resulting in peak folding or area shifts. This is not going to be much of an issue, just to sweep a large enough range. So there's also digital resolution, the number of data points. The FID is digitized. You have an analog signal that gets digitized. You want to max the dt equals 1 over, there's an equal delay between each point. So you want to maximize signal resolution. More data points increases acquisition time and experimental time. A longer spectral width requires more data points for the same resolution. So the longer you measure for, the better your resolution is. But so here you can see how the resolution gets better and better as we use more points. And your acquisition time needs to be long enough to allow the FID to completely decay. If it's truncated, you get wiggles. And amusingly, there's something called zero filling, where you improve your resolution by adding a whole bunch of zeros at the end of your data. And this is an 8K FID, and this is a 16K FID with 8K of zero filling. You get finer resolution because your resolution is proportional to the entire time you measure. Well, 1 over that time, the size of the resolution. But the longer you measure for, the higher the resolution. Well, this is basically completely decayed. So if you add a bunch of zeros, you can actually get a little more information out. And window functions can emphasize the signal or decrease the noise by applying a mathematical function to the FID. If your beginning stuff is good and your end stuff is mostly noise, you need it for resolution. You can apply this sort of decay function on it to squish the noise, but continue to have signal for resolution. You can either increase the signal to noise ratio or increase the resolution. You can either increase sensitivity or increase resolution. You cannot do both. So this gives you better resolution, worse signal to noise. This gives you better sensitivity, worse resolution. You need a flat baseline. You can fix this experimentally by applying various functions and subtract them. So a number of factors can lead to baseline distortions. Like intense solvent or buffer peaks, phasing problems, errors in the first data points, short recycle times, short acquisition times, or sequence. And you need to get the phase right, otherwise your peaks look weird and are hard to read. So improper phasing can give you these weird distortions in your baseline. So phase is due to the difference in the actual time and the 0 point. Now this can be fixed in analysis. You just need to correct the phase and how you're doing the Fourier transform generally. The other thing you could do is you can integrate the peaks And the relative peak intensity or peak area is proportional to the number of protons associated with the observed peak. So if you integrate over each peak, this is going to be roughly the number of protons associated. So this has 1 proton, this peak has 2. It's going to be twice the area of the first one. This one is 3. It's going to be 3 times the area of the first one. And you can use this to determine relative concentrations of multiple species present in an NMR sample. So the NMR timescale refers to the chemical shift timescale. So frequency units are in hertz. Timescale is going to be the inverse of that. So the exchange rate K could be related to the difference in chemical shifts between species. So slow, time scale, comparing the exchange rate and the difference in chemical shifts. And this is sort of what we're looking at. So with fast exchange, the observed chemical shift is the average of the individual species' chemical shifts. That's not going to be super relevant in our experiment because we're just going to be looking at pure substances. But I mean, this is a thing where peaks can sort of merge and interact with each other. So delta A and delta B, if K is much less than delta A minus delta B, the time scale is slow. It's intermediate. That's roughly delta A equals delta B. And fast, K is much greater than delta A minus delta. The delta observed is going to be F1, fraction 1 of D1 times fraction 2 D2, where F1 and F2 are the mole fraction of each species, and D1 and D2 are the chemical shift of each species if they're merging. If you have fast exchange, they'll merge into a single peak. This is when they're a little further apart in the coalescence. This is intermediate exchange, slow exchange, and no exchange. So as you increase the K exchange rate, you can go from 2 peaks at 40 hertz apart to a single peak in the middle. So you can also do multi-dimensional NMR, which is a series of RF pulses, delays, gradients, pulses, and phases. So in a 1D NMR experiment, the FID acquisition time is the time domain T1. In more complex NMR experiments, we use multiple time dimensions to obtain data and simplify the analysis. So multi-dimensional NMR experiments can also use multiple nuclei, like deuterium, carbon-13, and nitrogen-15 in addition to hydrogen, but they usually detect hydrogen-1. So this is a 1D pulse sequence. You have a pulse, and then an acquisition time, and then a recycling time. And then you do this a number of times, the number of scans times. For a multi-dimensional one, you'll have a pulse, a delay, and then another pulse. That's your second time domain. So you collect a series of FIDs incremented by a second time domain, T1. And the normal acquisition time is T2, and the Fourier transformation occurs for both T1 and T2, creating two-dimensional NMR spectra. They're 2D plots. In 2D NMR spectra, if you go along the diagonal, that would be normal 1D peaks. And off diagonal or cross peaks indicate a correlation between two diagonal peaks. So if you're looking here, because you often see these are often presented as a contour map, these are the normal peaks. These off diagonal peaks indicate coupling or NOE interactions between these two particular substances. I mean, groups of nuclei. So here, for example, is a 2D hydrogen noisy experiment. The diagonal peaks are basically the 1D spectra, which you can see along the sides. And then the cross peaks are ones that interact with each other. And the relative magnitude of the cross peak is related to the distance between the protons, physically. So you can correlate protons in this, from the diagonal that are physically close to each other. And here is one hydrogen carbon-13. It correlates all directly bonded carbon-13 one hydrogen pairs. And it generally requires carbon-13 labeling because the natural abundance is too low to do this easily. And here's a duo CSY one hydrogen experiment. This correlates all 3 bonded hydrogen-hydrogen pairs in a molecule. So you can see what hydrogens are next to each other. And it's possible to add extra dimensions, usually corresponding to carbon-13 or nitrogen-15 shifts. This is primarily used for analyzing biomolecular structures because it disperses various highly overlapped NMR spectra into 3D and 4D view. And you generally view 3D and 4D experiments as collections of 2D spectra. And for this, one experiment can take 2.5 to 4 days to collect. So this is a much more complicated thing to do. Now, the last thing to talk about is magnetic resonance imaging, or MRI. So here's an image of a brain with MRI, and you can see a concussion in it. Apparently, I'm no good at reading MRIs, but so magnetic resonance imaging, we were talking about that 2D stuff. Basically, it's multidimensional NMR imaging in a way, but they figured out how to basically encode position information in the frequency and phase of the signal, which allows you to basically get a slice, an image slice of whatever you're imaging by carefully designed gradients and field pulses. And then you can do various slices throughout, whatever you're imaging, like a person. But yes, there's a whole bunch of different gradient coils and RF coils and a superconducting magnet, because it's all about creating gradients in various directions and utilizing those to incorporate position information into the frequency and phase of the NMR signal. So you don't get as much like chemical information. You get mostly hydrogens be here, but for imaging, that's what you want to do. You want to identify things with hydrogens in them. And different peak patterns can identify different kinds of molecules better than others. So the biggest problem with MRI is that the magnet needs to be really big because you got to stick a person in it. And so that gets tricky. So what you have is you have this magnet bore with various RF and gradient coils around it. You have a superconducting magnet in a liquid helium bath. And you might have a liquid nitrogen outer layer, but I don't think they usually do. I mean, it's insulated, of course, but. And then this is kept cold with a refrigerator and a compressor. So the fundamental concept of MRI is by applying a gradient magnetic field, positional data can be encoded into the frequency of NMR peaks. And by adding additional gradients during more complex pulse sequences, more than one dimension of positional data can be encoded. So basically here, we're getting positional data this way in frequency. And by adding another pulse, we can actually get another direction in the phase. So we could have a pulse that we use to set the phase, which gives us our information about, we had a Y gradient and a pulse during a certain amount of time with the Y gradient on. That sets our phase. And then our frequency is determined by our X field gradient. So the frequency gives us our X position and the phase gives us our Y position. And that encodes 2 dimensions of information in the frequency and the phase. And by carefully controlling gradients in our pulse, we can excite only a thin slice in the Z dimension with the start of our sequence. So we're only looking at one slice. So by the use of a shaped pulse and a magnetic gradient along the Z-axis, the spins of the slicing of interest are flipped. So only one slice has its spin flipped. Then the flipped spins get excited by a pulse and allowed to precess in a field gradient along the Y-axis to encode the Y position as a phase shift. Then the Y gradient along the Y-axis is turned off and a gradient along the X-axis is activated, and the X position is encoded by the precession frequency. And there may be other pulses in there to do like a spin echo or things to extend the length of the signal or to just maximize, to excite things. MRI pulse sequences get very complex. So the real pulse sequences may use more complex processes to generate a clear image or target certain biological materials. So as you can see, these pulse sequences can be quite complex. And this allows you to get 3-dimensional images of stuff in quite possibly the least intrusive method possible. So MRIs give great images, are not very intrusive, but they are expensive. That is the end of our NMR stuff. So we will have the NMR lab on Thursday. And then we'll be done. We're done with all the lectures. Our last lab will be Thursday. So that it will be, we have a review. So I'll do a lecture of review, which I could do either Tuesday next week, Thursday next week, or Tuesday of the last week. I think I'll do it Tuesday next week just to get it done as soon as possible, and then you guys can take the test whenever you want. I'll get the test ready by the end of this week, so if you want to take the test early, you can. That sound okay to you guys?
Yes.
Okay. I'll see you guys on Thursday, and I'll go over the plans for the test and stuff then.
See ya.
Just for review. Have a nice day.